Hello everybody, this is another video from SAP Master channel. In this video I'm going to show you how you can calculate the base shear and seismic loads based on NBCC 2015. So NBCC is the National Building Code of Canada. So lots of you had asked me to teach you how to calculate the seismic forces and initially how to calculate the base shear and overturning moment. So today I'm gonna show you how you can do this with an example. This example is a medium rise masonry building. If you learn this stuff with masonry building, it won't be difficult for you to calculate it for your desired buildings. So today what we have, this is the building that we are going to calculate the seismic forces for. And as you can see here, it's a typical floor plan and vertical elevations are shown below for a 4-story mixed use, which is commercial and residential building located near the intersection of Granville Street and 41st Avenue in Vancouver, BC. The ground floor is commercial with a reinforced concrete slab separating it from the residential floors, which have lighter floor system consisting of steel joists supporting a composite steel and concrete deck. The front of the building is mostly glazing. It has windows, so it doesn't have any structural application. So at first we're going to determine the seismic force for this building according to the NBCC 2005. Equivalent static force procedure is the one that we're going to use, and a vertical force distribution in the east-west direction. We're going to find the base shear and overturning moment in the east-west walls, and we're going to assume that the floors are acting as rigid diaphragms and the strong north-south walls can resist the torsion. And then we're going to consider the torsional effects. It is also included in the standard. So we're going to consider the torsional effects in all walls and find the forces in the EW walls. And we're going to compare the seismic forces obtained with and without torsional effects. And for the purpose of weight calculation, we're going to use 200 millimeters blocks for northwest and 300 millimeter blocks for east-west walls. So I said northwest, it's north-south, I'm sorry. And all walls are solid grouted. And of course it is a conservative assumption appropriate for preliminary design, and the compressive strength is 10 megapascal. Grade 400 still has been used for the reinforcement, and the building is of normal importance and is supported on Class C soil. And we're going to consider limited ductility reinforced masonry shear walls. So it was a very long description of our project. You can always have a look at this one. It is including all the necessities that you need to know to calculate the base shear, and also it's going to be very useful for you. There are some specified loads here, and as you can see on the 4th floor here, on the roof level we have a 3 kilopascal. On 2nd and 3rd floor we have 4 kilopascal, and for 1st floor we have 6 kilopascal, and we're gonna consider 25% snow load, which is 0.4 kilopascal. And there is a 1 kilopascal allowance for partition walls and glazing. Okay, so this is the plan. As you can see, we have 2 walls here and 2 walls here. The heights are 5 meters for the 1st story, and the other 3 are 3 meters, and the span is 20 meters. Okay, so we're gonna start with calculating the seismic weight, which we are gonna call it W. So north-south walls are 200 millimeter thick, which will give us the W of 4.18 kilopascal for them, and east-west walls have 300 millimeter thickness. So The length of north-south wall, as you can see here, is 20 meters, right? And the length of east-west walls are 10 meters, as you can see here. Okay, so let's start with calculating the seismic weight of first story. As you can see here, the first story is this one. So when you want to calculate the weight, you have to include half of this wall below the story and half of the wall above the story. So this is what you are going to calculate. So you have a 5 meter divided by 2 and a 3 meter divided by 2, and also for here as well. So that's why we are having 5 over 2 plus 3 over 2 multiplied by 4.18, and we have two of them, and the length is 20 meters. Remember that when you have this one, you are calculating the half of weight of these two walls, which are 20 meters, right? And then you will have 3.68 multiplied by 2 multiplied by 10. These are these two walls. 3.38 is the weight of each, and then we have two of them, so we are multiplying them by 10 to consider the length of that. And then we will have the loadings here. So on the first floor we have a 6 kilopascal loading, right? 6 kilopascal is kilonewton per square meter, so we have to multiply it by meter to have a kilonewton, and if you calculate it, you will reach this number. Then for second floor, because the walls are in the same height, you will have this. Again, you have to repeat the procedure, but this time instead of 6 we will have the 4 as the force that problem has given us. And for W3 everything is the same, but for the last story we only have one wall underneath the story, so we won't have the second part of here. Okay, and now that we have all of these numbers, if you add all of them together, you will reach to the total weight. Okay, now then after calculating the seismic load, it's time to calculate the seismic base shear force. So for this one, you have to find the seismic design parameters used to determine seismic base shear, which is the acceleration in 4 different periods where you can find them from NBC. For example, I do have NBC here. I will simply search Vancouver and you will find it in the table C. So this is table C2. You're gonna find it in table C3. So let's go together and find it together. Okay, so as you can see here, I have the Vancouver, but it's important to find the exact location that we're gonna use. So this Vancouver is different from one that we are looking for. As I said before, our building is located at Granville Avenue and 41st Avenue, so you have to use these numbers. So as you can see, you have the acceleration in each different period of times or time periods. So you can reach all of these from Appendix C, Division B of NBCC, right? So let's go back to our problem. We have found them from right now I'm talking about NBCC 2005. The one that I showed you is NBCC 2015, so that may be there may be a little difference in the numbers. Okay, Then you have to choose in which site class you are building your structure. So for different site classes, we have different coefficients of FA, but for site class C, FA and FP are always equal to 1, right? So you can always find them again in NBC in table 4184B and table 4184C at NBC. You can find them. This is the importance factor. So ours is a normal importance building, so it's gonna be 1. And for MV, you need to find the higher mode factor, which is equal to 1 for a period of less than 1 second. You can also find all of them here. So if I search, I don't know if I search MV, I will find it or not. No. Okay, so we have to go back to part 4, and let me do that now. If we go to part 4, which is for, in the part that is for calculating the base shear, let me find it. Okay, this is the part that we are calculating the base shear and earthquake forces. So we have to go down and try to look for different parameters that you're looking for. So here it should be somewhere around here. So as you can see, the FA, which I told you, is always equal to 1 for site class C. For each different time periods, as you can see, it's always equal to 1. For C, it's always equal to 1. So if you have a building in another site class, you have to find them from these tables. And let's go and find MV. So this is for importance factor, as you can see in table 4185, and as ours is normal, so it's equal to 1. And if you go down, I'm sure, okay, so here we are also gonna need these two factors. We're gonna come back on them and talk about them later. Okay, here is the higher mode factor MV. So as you can see, when you have different T's, the numbers are different, and you also have to calculate this part first. And it's also different for each system, right? So here we don't have any of these. We have a masonry wall, so it's kind of other system. So we can come here and calculate the MV, which I have checked it before, so it's equal to 1. And okay, it said that it's a masonry structure with limited ductility shear walls for building height of 14 meters, right? So we need to calculate these two, or find these two parameters from the tables. So let's go back to this table and let's see if we can find the described system. So here it is for cold form steel. That's not what we are looking for. Masonry structure, and this is exactly what we are looking for. So it's moderately ductile shear walls, right? So the numbers are here 2 and 1.5. 2 for RD and 1.5 for RO. Let's go back to our problem. RD 1.5, RO 1.5. So what's happening? So it is limited ductility shear walls, not moderately. So we have to go again. and look for limited ductility. This is moderate. So if it's not ductile and if it's not moderately ductile, it is limited. And that's here. As you can see, 1.5 and 1.5 for each. Cool. So we have to calculate the time period, and we have the formula for calculating that, and it's also again different for different kinds of structure. Let me show that to you as well. So we have to go up, and in the beginning of the earthquake forces calculations, we have it somewhere around here. I'm doing this so you can do it with me, and in this way you will learn better how to even look for stuffs. Okay, I have it here. So fundamental lateral period of vibration of the building is as here. So we have a shear wall, and it is a masonry structure. So the formula is this one. By replacing 14 here, we will have a T of 0.36 seconds, right? We have the site design spectrum here, as I showed you where to find it at table C3. And for different ST is acceleration for different periods, right? FA is equal to 1 for all of them. So I have to calculate SA at 0.2. So at 0.2 it's 0.95. I will replace it, and it will happen for all of them. So the building period is 0.36 seconds, right? So I have to interpolate with between these two numbers, acceleration in 0.2 and acceleration in 0.5. By interpolating, I will get to ST of 0.79, right? And finally, we will have our formula for calculating the shear force. So ST here is the acceleration in fundamental period, which we calculate as 0.79, right? We will replace it here. MV was 1, I was 1, RD and RO was 1.5 each, and W. There are two lower bounds and upper bounds that you have to calculate before taking further action. So this is the formula for minimum shear force, and this is the formula for maximum shear force, which you can see it's higher than this one. So our shear force is higher than this one, so it's okay, and it is obviously higher than this one, which shouldn't be. So instead of using this V, we are gonna use this V, because this is the maximum one. And after finding our formula for shear force, we will only need to replace W here, which we have already calculated. So we have the shear force. And now all you need to do is to check and see if the equivalent static procedure can be used or not. Because if you cannot use it, you have to go with dynamic procedure. So according to the NBCC 2005, the dynamic method is the default method, but the equivalent static method can be used if the structure meets any of the following criteria. First, is it located in a region of low seismic activity where this amount should be less than 0.35? Let's check. In this case, our seismic hazard index is 1, and S is 95. It's higher than, so its criterion is not satisfied. Let's go to second one. Is it a regular structure less than 60 meters in height with period of less than 2 seconds in either directions? It clearly has less than 60 meters in height, and the period is also less than 2 seconds. So this criterion is satisfied. And the other criterion is that does this building has any type of irregularity? So this is an irregular structure, but it is less than 20 meters in height and the period is less than 0.5 seconds. So the torsional sensitivity should be checked to confirm that B is less than 1.7, which we will go and talk about that later, don't worry. So since the criterion B is satisfied, the design can be proceeded by using the equivalent static analysis procedure. So let's do it. We are gonna distribute this seismic force over the building height, right? So according to the NBCC, the total lateral seismic force is to be distributed over the building height in accordance with this formula. As you can see, this V is the one that we calculated as base shear, but what is this FT? FT is a portion of the base shear which should be applied in addition to force Fn at the top of the building, right? So, but you don't need to do that when your period is less than 0.7 seconds, which in this case it is, so we will normally have V multiplied by this portion. And finally, when you want to calculate the interstory shear force at level X, you can use this formula. And the bending moment easily can be found by this formula. So after you found the Fi in each story, you simply need to multiply by this portion, which here we have calculated all of them in our table. So the height is 5, 8, 11, and 14, and the Wx is calculated as before. So by simply multiplying these two, we will reach to this amount. Multiplying these two, we will reach this amount. And you can simply calculate Fx, right? So now, to calculate the Vx, which is interstory shear force at level X, as I told you before, all you need to do is to add these two together, and you will reach to this amount. To find this amount, you have to add these 3 together to reach this amount, and for this one, add these 4 together and you will reach to this amount. Again, for finding the overturning moment, all you need to do, now that we have all of these numbers, you only need to use this formula, which is very simple and straightforward, and we have shown it to you in this picture, and so it's very easily found. Okay, now it's time to find the seismic force in the east-west walls, right? So as you can see here, I have mentioned, due to the asymmetric layout of the east-west walls, the center of mass, which is called Cm, in the building under consideration does not coincide with the center of resistance. Hence, there are torsional effects in all walls. However, since the north-south walls are significantly more rigid compared to east-west walls, it can be assumed that the north-south walls will resist the torsional effects. As a consequence, it can be assumed that the base shear force in the east-west direction is equally divided between the two east-west walls. So, as you can see here, this is the one that we calculated. V was equal to 2900. So we will divide it by 2 and we will have 1450 kilonewtons. Similarly, the base bending moment in each wall is equal to the maximum divided by 2, right? And to find the seismic forces in the east-west walls, and by considering the torsional effect, a 3D analysis should be made. Even though the walls are considered uniform over the entire height, the contribution of shear deformation relative to bending deformation is different over the height. An approximate method that does not require a 3D analysis is to consider the structure as an equivalent single-story structure. The entire shear is applied at the effective height of HE, defined as the height at which the shear force VF must be applied to produce the base moment MF, which is, so the effective height is equal to MF over VF, which is 10 meter, right? So we have it here. In this model, although not strictly correct, will be used to determine the elastic distribution of the torsional forces as well as the displacements, but the top displacements of the wall is assumed to be 1.5 times the displacement at the effective height. The torque is a product of the seismic force and the eccentricity between the center of resistance and the center of mass, which will be calculated in the following table. So first, the center of mass will be determined here. As you can see, we have Wi and we have Xi for each of them. All of the parameters are revealed in this picture. You can see them here. There is no need for me to go into details, I believe, because it's very simple calculation. So you only need to have summation of Wi, Xi, so each of these together should be multiplied and divided by the total weight of walls, and then again you will do the same for Y direction and you will have it. So the center of resistance will be determined and the calculations are presented in table 3 here. So as you know, because we only have 2 equal walls in each direction, the center of resistance will lie between the walls, right? So you can see all of these. You may need to pause the video and think about these numbers, and if you have any problem understanding them, you can always write for me in comments and I will give you more explanation. So after calculating these amounts, everything will be found, and to find the error you only need to minus these two. So this one and this one, right? YCM is this one and YCR is this one. And in addition, the accidental eccentricity needs to be considered, which is equal to this number. And the total maximum eccentricity in the Y direction is equal to EY plus EA. So you only need to add these two, or you can always do the negative part. So it doesn't govern and it won't be considered in further calculations. If it was bigger, we would use this number instead of this one. And torsional moment is easily found by multiplying the shear force that the base shear force that we found, and ETY. It'll be very obvious. So the seismic force in each wall has two components, translationals and torsionals, which is shear force is equal to shear force of translational plus shear force of torsional, right? So for finding the translational component, you only need to use this one, and for torsional you will need to use this one. So we will need to find the J parameter first, which is the summation of kxi times cxy square plus the same for Y direction. And you can see translational and torsional force components for the individual walls in these two pictures. So in table 4 you can see summation of seismic shear forces in the walls due to seismic load in the east-west direction. Okay, so this was the first part of this video. If you'd like this, please subscribe and write in comments. There will be a part 2 for this video to go into details for more explanations about how you can use National Building Code of Canada to calculate the base shear and seismic loads in buildings. Stay tuned and don't forget to subscribe and invite your friends. Have a good day and bye bye.